All right, we're continuing on Chapter 6, Topic 5. And here we're going to do some applications, which are word problems, using rational equations. And our first two examples are sort of fill-ins. And the kinds of applications we're going to deal with are called word work problems, motion problems, and proportion problems. And the first one we're going to look at is work, and then we'll do some motion. And then we have the letters A, D, T, and 1 that are going to fit in here somewhere. Now, as we look at the booklet, it gives you the details, and I'll be putting up some of the major things so that as we go on, you'll be able to tie it into what's written here, but we're not going to write it all. So for number 1, it says, if lowercase a is the time needed for person capital A to complete the work alone, and lowercase b, which is right there, is the time needed for person B, capital B, to complete the work alone, and T is the time needed for both person A and person B to complete the work together, then what would this formula be here? And by the way, what they're setting up for you here is the major work formula that will be used in a number of examples coming up. So, if our first person is capital A, and they can get a job done in this amount of time, then this time over A is that person's rate. And if this person gets the job done in this amount of time, that would be person B, then we would put a T there. So this unknown time to their particular rate, unknown, which is the same time for this particular rate. And here's where the concept comes in that together working, they're going to get the job done in 1 unit or 1. So this is the basic work formula. Now, when I've taught this in other classes, we used a different formula, and I'd like to give you that too, just to see where this one came from. If, let's say, person A can get the job done in 4 hours, and person B could get the job done in, let's say, 6 hours, then how much time working together would it take for them to do the job? Well, the formula we used to use is this person's rate, which is 1 over 4, plus this person's rate, which is 1 over 6, is equal to 1 over T. That would be the time working together. So this formula that you may have used before, these are actually connected, because if you multiply every term by T, watch what happens. T, T, T. Here the T's cancel out, and now you have this formula. So the two formulas are related, but here they're putting the T's there already, and no fraction there. So whichever one you're going to use, they are connected. Okay, for example 2, it says problems involving motion use this formula. What are the letters of that formula? Well, you may recall we've used this before. Distance equals rate times time. And often we just see it this way. Now this formula we've used before, and we can play around with it. For instance, if we solve for the letter T, we just divide both sides by R, and we get T equals distance divided by rate. So distance divided by rate is time. Another version of it, if we divide both by T, the T's cancel out, and we get rate is distance divided by time. So 3 formulas. We call this one the main one. This is a modification, and this is a modification. So depending upon what you need, you would work with this basic, we call it distance formula or the motion formula. And now we'll get started on some actual problems. Okay, again, I'm not going to write out the whole problem, but I'll sort of summarize it. Horace can put the files in order in 2 hours. Janelle, it takes her 5 hours to get the files in order. Working together, how much time would it take to get the job done? Well, again, this is a work problem, and our basic form, and I'm going to use the one I'm more familiar with, but it converts to the other, as you may have seen. What is Horace's rate per hour? Well, he can get 1/2 of the job done per hour. Since it's 2 hours, his rate is 1/2. Janelle's rate is 5 hours, so her rate per hour is going to be 1/5. And together, we don't know that. It's going to be 1/T. This is the one I'm comfortable with, and you'll see it can become the other one very easily. So let's just do this one. So now what we're going to do is figure out, we want to solve for T, so we want to figure what's our least common denominator from our previous lesson. Well, think about it for a moment, and it's actually 10T. Now we clear the fractions. 2 goes into there once, into here 5 times. 5 goes into there once, twice. And here the T cancels out. So you now get 5T here plus 2T equals 10. Now notice the T's are back up there to the other formula they introduced. So this is going to be 7T equals 10. Divide both sides by 7. We get, converting this into 1 hour and 3/7 that it would take for them to work together. So they started you off with a very easy one. And as we look at it, again, 2 hours, 5 hours, so we know it has to be less than 1 hour if Janelle is helping. So that makes sense, and that's the answer. All right, going on to number 4, we have 2 types of printers. One's an inkjet printer, and the other is a laser printer. Now we know laser printers are really fast. So, what would be the strategy? Well, we know that together these 2 printers can do the job in 7 minutes, so it's a little different. So let's see what we can come up with. So the laser can do the job in, let's say, tea time. We don't know how much that tea is. The inkjet takes 10 times longer. And together, they can get the job done in 7 minutes. Now, as I mentioned before, when I do these, I have sat down with the booklet and on a piece of paper worked on them. Because they tell me the answer, but they don't tell me the formula. So I'm trying to be like a student a little bit here too, as I read these. So, let's go to solve it. What will our lowest common denominator be here? And so what a student is concerned with is understanding the problem, putting it into an equation, and then the next part is solving the equation where you need the skill of what's the lowest common denominator here. Well, it's going to be 70t. Now we're going to do some canceling. Here the t's cancel out. Here a t cancels out, and I can take 10 goes into there once, 10 goes into there 7 times. And then here 7 goes into there once, 7 goes into there 10 times. So we now have our new equation. This is going to be 70 plus 7 equals 10t. And now we're going to add this together. And we're going to divide by 10. And we get t equals 7.7. Now, the next thing we have to think of is, what does this mean? Well, we have to go to our original problem and say, what is the time it takes the laser printer to print up this job? If together it's going to take them 7 minutes, T, remember, is the laser printer. So this is the time it takes the laser printer 7.7 minutes, a little bit longer than when they did it together. And the inkjet printer would take 10 times longer than that, or 10 times that would equal 77 seconds. I'm sorry, minutes. Because this is in minutes here. So if this laser and inkjet printer work together, they would get the job done in 7 minutes. But the inkjet gets it done in 77 minutes working by itself, and the laser 7.7, because it takes 10 times longer for the inkjet. Lasers are really fast. Okay. Now I may have missed some of the bottom of that, and let me just give a moment or two at that. Okay. Okay, again, with the booklet and reading the problem, be very useful, but let's see if we can summarize. So Raoul can paint a bedroom in 5 hours, while Kim can paint that same bedroom in 3 hours. Working together, how long would it take to paint the bedroom? Well, what is Raoul's rate? 1/5. He can get 1/5 of the job done in an hour. So his rate is 1/5. Kim's rate is 1/3. It takes 3 hours to paint the room, so per hour they get 1/3 of the job done. And then together they're going to get it done in T hours. So 1/T. Now, once you start catching on to the pattern, these get a little easier. So let's do some of these. Number 6, Mariah can clean the horse stall in 6 hours, while Lindsay needs 10 hours to do the job. How long would it take if they're working together? Well, what's Mariah's rate? 1/6. What's Lindsay's rate? 1/10. And together they get the job done in 1/T. All right, number 7. It says there's a swimming pool that if it uses a pipe, it can fill the pool in 15 hours. If it uses a hose, it can fill the pool in 24 hours. How about if you had them both going at the same time? How quickly would the pool fill? Well, the rate of this one is 1/15 plus 1/24 equals 1/T. And those are the formulas. And we had in the previous chapter showed how to do them, and let's just help you a little bit on that, because setting up the formula is one of the main things, but then being able to work the equation. So what will your least common denominator be here? Well, 3 times 5 is 15, 15T. And the least common denominator here would be 30. You might say 60, but, I mean, 60 would work, but 30 is better. 30t. 30 is the least common denominator. 60 would be a common denominator, and if you were stuck, 60 would be okay to use. Now for this one, let's work on how to figure out the common denominator. Remember, we had a little exercise in a previous lesson where we said, take the prime factorization of the 15, and that would be 3 and 5, and prime factorization of 24. So, what's the greatest number of times the 2 is used as a factor in any one factorization? Well, here it's used twice. So 2 times 2 times 2 is 8. So we need an 8. What's the greatest number of times a 3 is used? Well, here it's used once. Here it's used once, so we need a 3. And we need a 5. So our lowest common denominator here would be, this is 24 times 5. I probably could do that somewhere here. And I think that's 120. So this is going to be, our common denominator here will be 120t, 120t, 120t. There you go. So 15 will go into there, 24 will go into there, and the t's just cancel out there. Now the answers are in the back of the book, and again, if I did every single problem, it would take way too long. And what we're doing here, though, is to work on converting word problems into the algebra. Well, we started off with some of the basics, and now we're building into some rather complex problems, and that's what I'm going to try to help you with. So in reading number 9, it says, Alex can detail a car in 20 fewer minutes than it takes Ryan. Together, they can detail a car in 21 halves or 10 and a half minutes. How long would it take for each person by themselves to detail a car? And if you don't know what that is, it's when you wash it, vacuum it, do the windows inside, maybe paint the tires with some things, and it's kind of an involved process. And it's more expensive than just running a car through a car wash. Okay, so here's what we know, that he can do it in this many minutes fewer than it would take Ryan by himself. And together, it takes them this much time. Well, as we look at this, it's going to be 1 over t plus 1 over, now this is t minus 20, and this together is going to be 1 over, you could have this down in the bottom or you could have this down in the bottom. I'm going to use this one. And you might say, wow, that's a new thing there. And it takes a little figuring out what's going on. So 1 over t, 1 over 20 minus, t minus 20, that's what our information is. This will be Ryan, this will be Alex here. And this is the total time. Remember, the t equals that, and t usually goes on the bottom. So what do we do to kind of fix this up a little bit? Well, let's treat this over here. This is 1 over 21 over 2, which means 1 divided by 21 over 2. So you might recall from way back in your algebra history or math history that when you are dividing a fraction, you have to convert the division to multiplication. So it becomes 1 over, this becomes times, the division's converted to multiplication, and we take the reciprocal of that. So this over here is going to become 2 over 21. Then we can get to work on things. Okay, so let's figure out what will our common denominator be. Well, it's going to be actually these three things. It's going to be, I'll put it out here, t, and we can put 21t times t minus 20. And we can put a great big bracket around everything, because now we want to multiply through to get rid of all of our fractions. So what happens? Well, here the t will cancel with this t, so this first term is going to be 21 times t minus 20. The t cancels with this t, and we're left with 21 times t minus 20. Plus, and I can cancel that one out, but we have to use that now for the next term. T minus 20 will cancel with this, so this now becomes 21t. And now the 21 will cancel with this 21, so we're going to get t times t minus 20. And you can see here we're going to get a quadratic equation because this is going to be a t squared. Now again, I'm not going to do these. What we're doing in this lesson is to set up the equations, converting from English into algebra, and then helping you with the common denominators a little bit. Okay. Now the answers are in the back of the section, so you can see what they come out as. Number 10. It says, Chris can clean an office in 3 hours. When he works with Hannah, they can get the job done in 80 minutes. How long would it take Hannah if she were working by herself to get the job done? Ooh. So it gets to be a little challenging. So we know Chris's rate. His rate is 1 over 3. Now we know when they work together, they get the job done in 80 minutes. but we don't know what Hannah's rate is. So Hannah's rate is going to be 1 over t. That'll be her rate. And then they get the job done together in 1 over, now you might say 80 minutes. But that's not good, because here this is hours and this is minutes. So you can't have, as I have put here, you can't have like different amounts of time. You can't have one thing in hours and another thing in minutes in the same problem, because it's sort of like fractions that don't have the same denominator. It's apples and oranges, minutes and hours, different. So I'm going to suggest that we convert the 3 hours into minutes. And how do you do that? Well, 3 times 60 is 180. So in 1 hour, it gets 1 out of So we've converted Chris's rate, which is 3 hours, into 3 times 60, 180. So his rate in minutes is 1 out of 180. Hannah's rate, we don't know. But together, they get the job done in 80 minutes. So there's our basic formula. And now we need to do some canceling out. Oh, first the common denominator. Well, 180, t, and 80. Now, it's probably a little smaller than this, but in a pinch, you can just use these 3 numbers. So here, the 180 will cancel out. Here, the t's cancel out. Here, the 80 cancels out. And now we're left with 80t, which is what I have here. I multiplied 80 times 180, got 14,400, and this equals 180t. So now it looks a little easier. So we're going to subtract 80t from both sides, and we get 100t equals 14,400, and we divide by 100, and that just takes out those last 2 zeros. So we get t equals 144. Now, what does that t mean? Well, it's the time it would take Hannah to clean the stable by herself. So we thought Chris was fast, but actually Hannah's doing a better job here. And there it is. And again, all they tell me is the word problem and the answer. I had to work on what is the equation, what's the common denominator, and I actually did this one for you because it's a little more challenging. All right, in this application, we're moving from work, and I didn't do them all, but hopefully you have a handle on it, to motion, in which we're going to use distance equals rate times time. Now I've written out a little bit of the problem. Here Beth is in a canoe, and she's going to canoe on this river, and the speed of the river is 4 miles per hour. So if you go down the river, whatever rate you can paddle at, 4 miles an hour is added because the river is flowing. This is sort of like jets in the jet stream. And she can go 6 miles upstream in the same time that she can go 14 miles downstream. So what is the speed of the canoe in still water? And again, you may have to read it again. You have a picture that I've made. You may want to make your own picture just to kind of get the understanding of what's going on here. And we're going to use this formula. So again, I had to read it and I developed the strategy. And what do you know about this? Well, we know the speed of the river. We don't know her rate. We know distance. One distance is 6 miles. And the other distance is 14 miles. Now we want to make an equation. What do we know is the same? Oh, look at right here. Time is the same. Okay. So what is time in this formula? Well, we said if we divide both sides by rate, we get that time equals distance divided by rate. And we know here that time equals time, a major key. And what did we say time was? Distance divided by rate. And there is the center of what we're going to use to solve this. So now let's set up an equation. Distance is 6 miles. Distance is 14 miles. Now, what we don't know is the rate, and that's the same on both. But here, we know that going upstream, your rate is affected that you're going against the current. So this is going to be -4. And then going downstream, your rate is going to be influenced that you're going with the current. And there is your formula. And by the way, I already knew this as I went into it, but what I was trying to do is to show you what initially, when I first read the problem, what I had to go through to figure out what was needed to get there. And now, what would be our common denominator? Well, it's R minus 4, R plus 4. R minus 4, R plus 4. So as we go to solve it, this will cancel out. This cancels out here. And we get 6R plus 24 equals 14R minus whatever that is. 4 times 4 is 16. 4 times 1 is 4. And 1 is 5. There you go. Okay. And if I look at my work here, I see I have done that already. Okay. So now what do we do? Well, we're going to transpose the 6R to this side. and that gives me 8r. I'm going to transpose the negative 56 to this side, and that gives me 80. Divide both sides by 8. I get r equals 10. So what is my answer statement? In the question they're asking, what is the speed of the canoe in still water? Well, in still water, the speed will be 10 miles per hour. Boy, she's really doing some good stuff there. And that's that. Okay, again, we had a number of other motion problems, but they're similar. You're going to have to figure its distance equals rate times time, and then determine which formula you're going to use. You're trying to find an equation and set it up. If I did every single one, again, the tape would be very long. So we'll try to give you a flavor of everything. All right, we're now moving on to what are called proportion problems. And one of the very common kind of proportion problems you have is where you have similar figures. Triangle ABC is similar to XYZ. So in similar triangles, the sides are proportional. So if you set up a proportion, then you're going to say 3 is to 10 as x is to 8. So that's your basic proportion. And hopefully one of the skills you had in class is when you did your proportion lesson, you had something like that A is to B as C is to D, and then you're taught that you can cross multiply, that AD equals BC. And A and D are the extremes, and B and C are the means. And we say the extremes, the product of the extremes, A and D, is equal to the product of the means. So we can then use this to solve for any particular letter. So here, this is going to be, let's do this one, it'll be 10x equals 24. And then you just divide by 10, and you get x equals 2.4. So this one's 3, this one's 2.4. And I didn't make my diagrams proportional, but they serve the purpose to illustrate. Okay, you can also use proportions, let's say in example 21, where Terry wrote 72 pages for a novel in 12 days. Well, if she kept this up, how many pages would you expect that she writes in 16 days? And again, you're just going to cross multiply, get this, and then divide by 12. Now, the key to any proportion is it has to be pages to days. Pages to days. Otherwise, it's not a proportion. You can't flip that. It has to be pages to days, pages to days. Now, number 23 is interesting. I used to be a biology teacher, and this would be sort of the thing in field ecology we would work on. Let's say you went out to a lake and you trapped 25, let's say, what are we catching here? Trout. And you tag them. Okay? So you catch 25 trout and you tag them. Did you catch the whole amount of trout in that pond or lake? And the answer is no, but you got a sample. Then at a later date, you caught 18 trout, and of those 18, 10 were tagged. So you're wondering, how many trout are there in the lake based on your sampling? So here again, the key is how many were tagged. So the tag is to the total population, tagged is to the total population. Here, a student is very easily could flip those, and of course if you did that, that would be incorrect. So when you're setting up a population, you might say, what are you setting it up? Well, tag to total population. Tag, you didn't know the total population. So when you went out another day and you got another sampling, that was in a sense a representative of your total population, then you had 10 of those tagged. So that's the ratio. So on that first day, you did pretty good getting those. This is just an example. And again, you would find it by cross-multiplying and getting an answer. The answers are in the back of the chapter. And here what we're trying to do is to show you the methodology. Well, good luck on this. And I know students have problems with word problems, but give it your best shot.